Hey guys, welcome back to another episode of Simuleos, the only channel on Twitch, well, okay, the only channel on Twitch that was, at least at some point, exclusively devoted to computational physics, but things have kind of changed just a little bit. Lately we've been kind of broadening our horizons and doing a whole bunch of different things. Luckily today, we are doing computational physics again. I'm super excited because today we're working on a pretty difficult algorithm, and I just wanted to point something out real quick. So, as of yesterday, oh, there's my stream, I put a link on Twitter, or not a link, a poll on Twitter. And on this poll I asked, which of these is most interesting? Magnets, drawing with code, dusty plasmas. Looks like there are 6 votes. Most people said magnets, so that's what we're going to do. This simulation is one that I'm not, how do I put this? I'm not very good at, but I know I'm not very good at it. So the idea is that I will be, first of all, doing my own thing, on my own for what I can. And then when I cannot, I will show you guys the links from where I'm getting some of the material. And we might switch to Julia for a little bit, then go back to C++. We might go back and forth a little bit. Because again, I know what the DMRG algorithm is, and I kind of sort of understand it, but I don't understand it enough to be able to do it on my own as of this point. So I'm kind of working off of other people's code. It's a very well-known code. Lots of people know a lot about it, so that's kind of one of the reasons why it kind of makes sense to work off of other people's code to start. Okay, so making sure everything is good. It all looks good to me. So let's go ahead and ls here, cd into projects, Simuleos, and then we need to make a new directory, which is DMRG. There we go. cd into DMRG, and do the same thing over here, cd projects, Simuleos, DMRG. Good. Okay, let me do a quick git pull to make sure there weren't any changes since the last time I have been on the Simuleos directory here. Not that it really matters that much. Let me see what happened. Local changes to the following files overwritten by merge, conjugate gradient, eigen, CPP. What do we have? Okay, let me go ahead and fix this real quick. Sorry about the yawn, guys. Okay, so let's do CD. Where would this be? Linear algebra, so LA, conjugate gradient. Oh, this could be an LA. So then we'll do get diff, conjugate gradient. Let's do eigen.cpp. Okay. Well, let me just do this then. CP. Let's do MV. Hey, Gustrun. Conjugate gradient. I know there's like a git stash or something. I'm just very bad at git. At git. So conjugate gradient eigen.cpp. Other.cpp. Okay, now let's do git pull. I know I could have used git stash, and I think it would have just been one quick command. Okay, so now we're gonna do move. Let's do other. Hey, perfect beast. To conjugate. Oh wait, where am I? ls. Okay, so let's move other to conjugate gradient dot cpp. Oh, I see what happened. Let's cd dot dot ls. We have stuff in the LA directory because it was not moved. It was not in the Git didn't know about it. So let's go into the archive. Archive. Actually, it should all be fine. I think it should all be fine. Yeah, we're good. We're good. Because what I did that I had not pulled yet to this machine is I created an additional directory which is called the archive, and I have 2 of them. Let me cd into lowercase archive. ls. Yeah, there's nothing in there. Let me remove -r archive. I don't think that's a part of Git. I think that's fine. I think that was there before. Ooh. Uh-oh. Maybe there's no way for me to tell. Unless I go on GitHub. 1 second, guys. GitHub.com. Go to Simuleos. Good. Okay. So let's go to Simuleos. And yes, so they're just capital archive. Sounds good to me. Okay, so let's ls here. So all of these additional guys here, so ants, archive, base drop, BC, CUDA, DMRG, FTTD, function integrate, all this kind of stuff, they're just because we have local files that are not tracked by get. So that's the only reason they're there. Okay, sounds good to me. So let's cd into DMRG, and should be ls. Yep, absolutely nothing as of now. So let's take a minute and talk about magnets, what they are and why they're cool. So open up Zernal first and go from there. So it's been a while since I used Zernal. I think I used it yesterday a little bit. Yeah, I must have. Okay, so first of all, the type of magnet that we're working on today is a one-dimensional magnet. So I guess we should kind of sort of get started. I'm going to hand wave my way into talking about magnets. So magnets. Like I said yesterday, magnets are kind of complicated. Here's the thing, we can wave our hands at them and we can say, okay, this is kind of how they work, and that's perfectly fine. But when we start talking about how magnets work in particular, it gets kind of complicated. So first things first, let's describe magnets by their spin. Rather, let's describe them as these kind of weird vectors that are pointing in some direction, okay? Now, when I say this, I don't think it really makes sense as of now, but give me just a minute to describe this. So, like I said yesterday, and I kind of breezed through it, so I want to kind of take it a little bit slower. If we have an atom, we have a nucleus of the atom, and we have electrons on the outside of the atom. So I guess I'll draw those in red, just kind of some sort of dotted line on the outside. Okay, so the nucleus is not really doing very much. We can assume that the nucleus is steady. It's in one single position. Hey chicken skill, the electrons on the other hand are moving in some clear direction. And we'll say that clear direction is maybe counterclockwise. So it's going in this direction around, right? Now, if we have a charge that is moving, we generate a magnetic field. And so the reason for this is Maxwell's equations. Now, I understand what you're thinking. When I say the reason for something is due to some sort of fundamental equation or something like that, that doesn't really make physical sense, right? Because the equation is not the fundamental thing. The physics is the fundamental thing. However, Maxwell's equations are pretty good at, how do I say, simulating the physics in giving us the physics that we want. So the equation in particular that I'm talking about is del cross B is equal to mu naught I plus mu naught epsilon naught dE over dt. And if you don't know what the math means, that's perfectly fine. Basically, the idea is we have B, which is a magnetic field, related to I, which is a current, and some sort of constants. And so I'm going to kind of mark in red everything that's not important. This is not important. This is not important. So the idea is that we have I related to B, and it's del cross B. So the del cross is something known as a curl, and it does exactly what you would expect. It curls around the object. It gives you a field that goes around the object. So if we have a wire, here's a wire, and we did this equation, we had some sort of current moving along the wire, we would have a magnetic field that wraps around the wire. And this is again because it's the curl of B, so it's curling around the object at which we're pointing to, and that would be the current in this side. Okay, so that was kind of long, but here's the idea. If we have a single, let's say, electron going around the atom, right? Let me get a quick drink of water. Sorry about that, guys. I don't know what it is. I always get water before streaming, right? But somehow in the middle of stream, I'm still super thirsty. I guess that's fine, but it's like only 10 minutes in. How am I that thirsty? Currently browsing your PhD programs. Cool. Let me know what you think. Okay, so here's what we got. If we have a single electron moving around this way, it ends up being that we have a magnetic field being generated around that object. It's fine. So let's take this guy and let's split him this way. Okay, by that I mean, let's put the atom here. I guess I'll draw it down here. Let's put the atom nucleus here, and then let's put the electron either going here or here. Where here it's going into the board, which I'm going to say is an X, and this is going out of the board, which is a dot. If you're not familiar with the notation, basically anything that is a dot that looks like an eyeball and it's looking right at you, that means it's coming out of the board. If it's a circle and an X, that means it's going into the board. Okay, so now we have a magnetic field that's being generated. This one's going into the board, so it's being generated going this way. And then we have a magnetic field on this side, which is generated going this way. And this way, if we add, hey iCare, thanks for coming in. If we add these guys together, we have a magnetic field that is in total going this way. Okay, so in this way we see, sorry for all of this, we see that we can generate a mini magnetic field. I'm going to say mini B field. Oh my gosh, I cannot write. B field with every atom. Okay, so that's the point. We have a whole bunch of mini magnetic fields kind of going in this direction, generated by every atom. So now what can we do with this? If we have a whole bunch of atoms together, then what we can do is we can kind of assume that if we have some sort of crazy thing like this, every single atom has some sort of arrow pointing in some direction that is related to the magnetic field. So let's do this. I don't know, I'm just pointing these guys at random for now. Okay. I don't know, something like this. Okay, now we have all these atomic atoms and they're all kind of pointing in some direction. If we give it an external magnetic field, you know, we give the magnetic field something. So here I'm going to draw the magnetic field going in this direction here. Now all of these atoms, which were before moving in their own separate directions, are now all going to want to align to this magnetic field. So this means that after we put in the external magnetic field, we're going to see all of these atoms shift so that they are pointing up. Something like this. I'm hoping this is making sense, guys. So the idea then, and the reason for the alignment is something called like a dipole effect, I think. So the idea is that a dipole, if you put it in an external field, it's always going to oscillate in that external field. So this guy always wants to be aligned to the magnetic field, like so. So this means that all the, I guess you could say, all of the atoms which were facing some other direction, or all the electrons around the atom which were facing some other direction, now all want to align with the magnetic field. And that, in this way, we can create a magnet by applying a magnetic field to a metal or something like this, right? So the idea is that with these spins, by flipping them and putting them all into the same direction, we can actually generate a magnet, right? A magnet that you'd put on the refrigerator or something like that. The point is, we have a difference between permanent and non-permanent magnets. Permanent magnets, no matter where you look in the magnet, all of the atoms are all kind of facing the same way. You all have the magnetic field from each of the little structures inside of the magnet facing in the same direction. Non-permanent magnets, the atoms only face in the same direction if we have an external magnetic field. So you kind of have to, gosh, I cannot speak today. You kind of have to draw the distinction there. The other thing is, what was I going to say? I don't remember. Okay, so here we have all these guys doing their thing. Let's do, oh, this is it. Magnetic fields can only be generated by moving electric fields, right? So you have to keep that in mind too. That's why we say it's the electron that's moving around each atomic nucleus that's doing this, right? So the idea is that we have an electron going this way, which generates a magnetic field that's going up, and then we can work with the spin of every object, right? Okay, so we see that anytime we have these kind of weird vectors that are pointing in some direction, we can generate some sort of magnetic field with those. And so this is where we enter in, wait, I just did this, the DMRG algorithm, which is what we're going to be working with today. The idea is it is magnetism, so magnetism B in 1D. So here's how it works. We have, okay, so we have a couple initial sites. I'm going to draw 4. Now, you could technically start with a different number, but for now, because we're using a pretty simple algorithm, I'm going to start with 4. The idea is that there are 4 spins starting in some direction. I'm just going to start them all up. Okay? So we have some spin starting all in some direction like this. Okay. Now, hey Nakib, so the idea then is we take these 4 spins and we begin to make the system bigger and bigger until it fits an entire 1 or in some cases 2-dimensional system. Long time no see. Would you update me on what you've been coding lately? Well, Nakib, I've actually been gone for the past like month and a half, so I just started streaming again today, or yesterday actually, and so the only thing I've done so far on stream is related to a, what was it? It was a, I wanted to do some drawing with this program called Cairo. It was actually a lot of fun, and I intend to do it again sometime, but not today. Today we're working on a new algorithm which should be a lot of fun, and I'm describing it right now, so I think you haven't missed that much. But it's good to be back, man. Thanks for coming back. Should be a lot of fun. Let me know if you have any questions. Okay, so now we have all of these particles kind of moving in some direction, right? And the idea is that we kind of work with these guys. So first we start with these, and we put them into different blocks. We say, okay, well, we're going to have a Hamiltonian, which again, as I described yesterday, was a way to describe the kinetic and potential energy of a system. And we're going to split it into 2 blocks, a block on the right, or left, a block on the right. Block on the left, block on the right. And then what we do is we expand these blocks outward into the system that we want them to be in. So we first diagonalize both blocks in order to find the eigenvalues. And once we find the eigenvalues, we then use those eigenvalues in order to generate new blocks, right? So if you're not familiar with what eigenvalues are, how to diagonalize and things like that, that's kind of what we're going to be working on for most of today. And once we get that done, we're going to take a step back, rather, we're going to take a step forward and start working with the DMRG algorithm in full. And that's kind of the idea, right? So, I guess there's some physics I kind of glossed over, and I think that's okay. Because in the end, we're going to have to gloss over some physics, and I'll get to it when I get to it. So let me do new page before. What we need to know now is that a Hamiltonian, which is typically described as a capital H, sometimes with an operator sign, is basically your kinetic and potential energy operators. So when I put a little hat on top of it, some people naturally assume I mean direction, but I don't. In this case, I mean an operator. So an operator is something that acts on something else. D by dt, which is the partial derivative with time, is an operator. Because in and of itself, it doesn't mean anything. It has to be related to another object to mean something. Del is another operator. Or, yeah. So this is another operator that works on things. And of course, you know, whatever other d by d whatever, those are all operators too. So the idea is that we have these kinetic and potential energy operators that will be acting on an object. So if you're familiar with the old Schrodinger equation, if I can even spell Schrodinger. Okay, Schrodinger equation. It's something like this. H psi is equal to E psi, right? And this is because we have potential and kinetic energy operators. So the operators are kind of essential here. This is equivalent to saying we have d over dx, let's see, h bar squared over 2m, then plus, let's see, 1/2 m omega squared x squared is going to be equal to I h bar d over dt of, and let me add in these guys here, psi, where this is equal to the energy up here, and this is equal to the Hamiltonian. Okay, good. So now we have the Hamiltonian here, and the idea is if we take a Hamiltonian that is sufficiently complicated, and we diagonalize Hamiltonian, diagonalization, which we're going to cover in just a bit. If we diagonalize the Hamiltonian, diagonalization, we get the eigenvalues. And with the eigenvalues, we begin to understand the dynamics of the system itself. You can kind of think of the eigenvalues of a wave function or something like that, the eigenvalues of a Hamiltonian as the ways in which the system can oscillate. So, for example, you could say, okay, well, it can breathe in and out in this way, or this way, or this way. It is the way in which the system can move. And then everything else is kind of going to be like multiplicative values or different, I guess, summations of these methods in which the system can move, right? So we say, okay, it can move in this way. So all of the other states are going to be mixtures between the two ways in which it can oscillate. So what we need to do first, before moving into any of the cool physics stuff, is we need to talk about what diagonalization is and how it works. And so here, where I'm actually going to take out some notes because I wanted to make sure I had a matrix that was diagonalizable first, so I didn't accidentally pull one that wasn't. And then I was going to show you how to do it analytically. After showing you how to do it analytically, I was going to do it numerically. And then once we do it numerically, which is in code, we're then going to move on to the DMRG algorithm, which might not be until tomorrow, depending on how far we get. So we'll see how far we can get. Okay. Oh, by the way, so most of the DMRG stuff that I'm pulling from is from a paper written by Stephen White, the original guy who wrote the DMRG algorithm, and it is the following paper. Density. One second. Density matrix algorithm for quantum renormalization groups, and it's going to be this one right here. So I guess I will go ahead and link this one to you guys in chat. Yep, this looks like it. And this is going to be where I get most of the density matrix renormalization group stuff from. That's where I got the intuitive physical understanding of what it is. And then the following, let me go to simple DMRG, is going to be where I found most of the DMRG stuff. So here it is there. So if you're interested in any links on how this works or what the point is, there you have it. It's right there. And then, oh, they also have some code on github.com, which is for the Julia stuff, which I printed out right here, so we can basically work off of that. Okay, so now, let me go ahead and get started with the other stuff. Alright, so I've got to figure out, this might not have been the brightest decision of mine. I've got to figure out how to move all of these papers around such that this actually makes sense. Okay. So, let me put this over here. Alright, this may or may not work. One second. Oh gosh, it didn't work. Oh shoot. I'll put this there. And this here. Okay, so diagonalization. Let's go ahead and pop over to the next desktop and work on the Zernal page one more time. Okay, so new page before. The reason people do diagonalization because it really helps find what are known as eigenvalues of the system. And with eigenvalues, you can find eigenfunctions, which we'll get into in just a second. So let's very quickly talk about analytical diagonalization. Okay, so first things first, let's say we have a matrix, any matrix. I'm just going to say, put a whole bunch of dots here. It has to be a square matrix. These are all values. They are not zeros, but just pretend there's some sort of random values. In order to diagonalize the system, what you do is you basically subtract out the identity matrix times these lambdas, where there's zeros everywhere else. And then from that, you solve for lambda by performing a, what's it called when you condense a matrix? By performing a, oh crap, I don't remember what it's called. If you take a matrix of 2, 1, 2, 3, 4, it's going to be 1 times 4 minus 2 times 3. So that's going to be 6. But that doesn't matter because I don't remember what it's called. Let's see, reduce. Is it called? No, I think reduction is another thing. But I think there is a way to find, like, diagonalize things with reduction. Let me see. Matrix manipulation. 1 second. What can we do? Matrix product. No. Square matrices, all matrices, matrix product, inner product, outer product, algorithms. No, I want to do row, column, vector, square. How do I not remember this? Determinant. Thank you, Nakib. I'm sorry, and Gustorn too. It was totally the determinant. I'm very sorry, guys. for some reason completely out of it today, and I didn't realize that. Okay, there we go. Determinant. Okay, so I'm going to take a square matrix that I wrote down on the side so that I know that it is diagonalizable, and do this quick example. So it's going to be this one. 1, 2, 0. 2, 1, 0. And then 0, 0, minus 3. Okay, so the first thing we do is we add in the lambdas on the diagonal. So it's going to be 1 minus lambda, 2, 0, 2, 1 minus lambda, 0, 0, 0, minus 3, minus lambda. Okay, if we perform the appropriate operations here, again, the easiest way to do that is to kind of put your finger over this one, and then to perform the determinant of these guys. So we have 1 minus lambda, then we have this squared, and then we have minus 3 minus lambda. Then we have subtracting 2, and then 2 times negative 3. So this is going to be a 4 times negative 3 minus lambda. Okay, and then the last one's just going to be 0. So now we just have to basically solve for lambda, right? This isn't so bad. We just have to expand everything and then go back out. So what do we need to do here? We're going to do 1 minus lambda squared first. So it's going to be 1 minus 2 lambda plus lambda squared minus 3. It's called Cheo's law. I'm actually not sure what Cheo's law is, but I will trust you on that one. Minus, let's say, 12. Oh, actually, it's going to be plus 12 plus 4 lambda. Okay, so now let's go here again, and we're going to have to do this times minus 3 minus lambda. So it's going to be minus 3 minus 6 lambda plus... Oh, nope. I'm just really bad at math. This might not work out the way I'd expected it to. Then we do minus 3 lambda squared. Then we have plus lambda. Minus lambda plus 2 lambda. Then we do squared minus lambda cubed plus 12 plus 4 lambda. Okay, this is going to be really interesting. I think I screwed something up. So minus 3 plus 6 minus 3 minus 1 plus 2 minus 1. Okay, good. So maybe that's right. Minus 3 plus minus plus minus. Okay, so now we add all the terms together. So we're going to get minus 3 plus 12. So these guys are going to make 8 or 9 together. Maybe I did screw something up. Okay, so plus 6 lambda. Then we have minus lambda plus 4 lambda. And I also, yeah, that's fine. So plus 6 minus 1 is going to give you 5. And then plus 4 is going to give you 9. Okay, so now we have the lambda squares to deal with. We have minus 3 and plus 2. So we do minus 1 lambda squared. And then finally we have the lambda cubed over here, which is going to be minus lambda cubed. Now, we can, in some way, shape, or form, we can factor this out to give us these 3 parentheses guys that we had before. I'm not really that good at factorization though. What I do have though, is I do have the answers stored somewhere. So I'm going to pretend I can factorize. And I will tell you that it factorizes into the following. So lambda plus 3, lambda, 1 second, minus 3, and lambda, 1 second, plus 1. Okay? So what I'm going to do very quickly is make sure this multiplies out to what it's supposed to. So lambda minus 3, lambda plus 3, lambda plus 1. Okay, these two together will give you lambda squared minus 9. Then if we multiply by lambda plus 1, we will get, let's see, lambda cubed, which is already wrong. Yeah, that would have to be a minus lambda minus 1, which is the same as lambda plus 1, which should give you the same. Anyway, we'll see what happens. Okay, so lambda cubed, minus 9 lambda. Oh, I might have screwed this one up. Then we do plus lambda squared, and then minus 9. Okay, what did we have on the previous page? We had plus 9 lambda, minus these two minus... Okay, so we had 2 positive 9s and 2 minus 1s. We have 2 negative 9s and 2 plus 1s. So this is just the negative of what we had before. So this does check out. And we know that the eigenvalues in this case are going to be... I'm just going to solve it as 3, negative 3, and 1. Okay? Did that make sense to everyone? Did I do something a little bit too fast, or maybe if I'm going a little bit too slow? Let me know, and I can kind of change the speed accordingly. But basically, this is just finding the eigenvalues of the system. Now, let's do something else. Let's do the eigen vectors. So with the eigenvectors, the idea is that we go back to the matrix that we started with, right? So if you remember, that is going to be this guy right here. Oh, we started with the lambdas in. Okay, so this is going to be 1 minus lambda, 2, 0, 2, 1 minus lambda, and 0, 0, minus 3, minus lambda. So it's going to be 1 minus lambda, 2, 0, 2, 1 minus lambda, 0, 0, 0, minus 3, minus lambda. In order to find the eigenvectors, what we do is we add in basically all of these eigenvalues that we had before. So to these lambda positions, and we find a vector. I'm going to do one of them, and then we'll kind of go from there. So the one I want to do, I'll do negative 1. So let's plug in negative 1. Plugging in negative 1 to this guy right here, which I'm going to draw a little socket plug thing, is going to give us 0, 2, 0, 2, 0, 0, 0, 0, minus 3, oh, sorry, minus 4. Oh, minus 2. There we go. And then what we do is we multiply these guys by x. So x1, x2, x3, and we set it equal to 0. So this is going to give us something that is a little bit weird. In fact, I think this isn't right. One second. 1, 2, 2, 1, 0, 0, negative 3. Okay, so this seems wrong to me. It's because I screwed up. 2, 2. Come on, guys. Obviously, 1 minus negative 1 is going to be 2. Okay, good. That's just 1 plus 1. Okay, so now we do page, new page before, and we have 2, 2, 0, 2, 2, 0, 0, 0, negative 2. Okay, let me check to make sure this is exactly what we had before. It is. Now we multiply by x1, x2, x3. Then we set this equal to 0. So we just do the multiplication here. Yeah, I'm sure. This is, again, just some... it is kind of basic, but I keep screwing it up anyway. So it's going to be 2 times x1 plus 2 times x2 is going to be equal to 0. Then we have 2 times x1 plus 2 times x2 is going to be equal to 0. Same equation. Then we do negative 2 times, what do we do? Negative 2 times x3 is going to be equal to 0. So we see here, obviously, immediately the x3 is going to be equal to 0. And then we have these two guys to deal with. And it's clearly obvious that if they equal to 0, that one has to be the negative of the other. So we could choose literally anything for this, but the one that I'm going to choose because it's the easiest for our eigenvector corresponding to the negative 1 eigenvalue. So if lambda equals negative 1, we have an eigenvector that is 1, negative 1, 0. Now, literally any vector that could satisfy this particular equation will give you this thing, right? And that's fine. But we're just going to choose -1, 1, 0, or 1, -1, 0. It doesn't matter. I think I said this one. There we go. That's what we got. Now we can do this for each of the other values, and we find this. So if we choose lambda equals -1, we're going to get 1, -1, 0. If we choose lambda is going to be equal to 3, or lambda is equal to -3, we get 1 second. We get in the case of -3, we get 0, 0, 1. And in the case of 3, we get 1, 1, 0. So these are our eigenvectors. And again, the eigenvalues are kind of, I always think of them as ways in which the system can oscillate. It can kind of move in some directions or something like that. And this is because in classical mechanics, when we find the eigenvalues, they're basically just that, ways in which the system can oscillate. So, now, onto the actual algorithm. New page before. Now here's the thing. If you pull up any linear algebra library, there is going to be some sort of, I guess you could say, algorithm in that to do the diagonalization for you. And that's perfectly fine. In fact, I think that's a very good thing, and I will be using those diagonalization libraries from now on. However, because diagonalization is such a big thing in physics and it's so useful for so many different things, we have kind of created our own algorithms for them. And these are the algorithms that you'll find in... when I say these are the algorithms that you will find in the linear algebra libraries. So one rather old one, but kind of famous one for diagonalization is the Zaz? Oh, is that right? Now I have to Google it. I have to Google this one. Sorry guys, 1 second. The cause. No. I had it wrong to begin with. Lankzaz. I don't know how to pronounce it. Now with sound effects. Yep. Okay, so now we have the Lankzaz algorithm. Now, I don't know how to pronounce this, so forgive me if I'm pronouncing it incorrectly. But the algorithm is not so bad, right? Lando? Oh, is that it? The Lando, let me think. You would know, I wouldn't. Anyway, here's the algorithm that we're going to use. It's not a very difficult algorithm to learn, but it can be kind of tricky. So what I'm going to do is I'm going to kind of write it down in pseudocode before implementing it in actual code. I think this is probably a good practice for most people who are trying to learn how to code in the first place, to kind of write down the code in pseudocode and then go from there. Now, I have this written down somewhere, and I'm doing my best to figure out how to put all the books on the table without disrupting the feng shui of my room. Now that I have feng shui, but that's okay. Give me 1 second to move everything around. Okay, so I think we'll be able to get through the diagonalization, and then we'll be able to approach the DMRG stuff, but I don't know how far we'll get from there. Okay, so here's how the algorithm kind of sort of works. I'm going to write down all the steps, and then we're going to implement it. So first things first, what we do is we create a matrix that is not the diagonalization matrix. So let me see, how do we do this? If we want to, so diagonalization. Okay, so if we want to do the diagonalization, here's kind of a pseudocode to work with. First thing we need to do is create a random matrix with a whole bunch of elements to it. So in this case, we might be using like maybe 200 or so elements or something like that. But the idea is that it's random. And here, I'm just going to draw it out this way. This half is where we generate things, and the other half we're going to copy over. So this half is going to be physically generated, or not physically, but it's going to be generated. And this half is going to be copied over. So we're going to have basically a symmetric matrix. Okay. So now what we do is we refine everything to work from here. So we have a huge matrix, hundreds of elements big. And then what we do is this. We have some sort of, let me see. We have some sort of additional steps from here. So the first thing we do is we say, okay, we have, we create some random numbers. Here, let me split it into steps. So we have 2, and it's split into a couple steps. We say j equals 0, okay? And where j equals 0, we set r naught is going to be equal to a random vector that is this size. So we'll say a random vector of some sort of length, right? So this is going to be r vector, okay? So now we have an r vector, which is the length of the number of elements that we want to work with. Okay, and then we give it another value. We say b is going to be equal to square root of r squared. So this is going to be the magnitude of r. And then after that, we say q. Q is going to be equal to r hat, which is going to be r vector. Vector over the square root of r naught squared. Okay, so now we have our q, we have our b, we have everything else. Finally, we create an a from this, which is going to be equal to q transpose. Which is just going to be a whatever those things are. And then a, which is going to be the matrix in which we want to diagonalize, which was generated here. Okay, and then q. Okay, now we do this again for j equals 1, and we basically generate the same thing. So j equals 1, we say r of 1, let's see, is going to be equal to, let's say it's going to be a dot q1 minus q. This is from the previous q, so we'll just kind of keep it q. Dot q. Okay, and the idea is we keep generating these r values, these b values, and the let's see, we keep generating r, b, and q, and this is an a. So r, b, and q, and recalculate a over and over and over again until eventually we get to the point, which I think is usually we only get to j equals 2 or j equals 3, where we generate q, a big Q. And we generate the matrix that we need from that. So the big Q is just going to be this. All of the Q's added together. So Q1, here, let's do this. Q2, Qn, and it's going to be some giant matrix that composes each of these large Q matrices there. And that's kind of all we do. It doesn't really make very much sense here, but what I'm going to do is when I code it up, I think it should make a little bit more sense. But again, the idea is that we keep generating these kind of sort of physical quantities, right? So we generate the magnitude of our R value. We calculate the vector, which is, or the R hat value, which is kind of the direction of the R value. And then we calculate this little A matrix in the end. And then we just kind of keep working on it. And the idea is that the algorithm ends when we have diagonalized our matrix. So what I want to do is I want to just try to implement this. I have some pseudo MATLAB code here written down. And what I'm going to do is I'm going to try to put it out into some C++ functions. And we'll see how long that takes, see if we can do it in an hour. I think we can, but there's probably going to be something that breaks. As always, this channel is known for breaking things. And then we'll kind of work from there. As things break, we kind of fix it and stuff like that. As it is now, we've kind of spent 45 minutes talking about one thing or another. So I think it's about time that we get started working on the actual code. Forgive me if this was a little bit quick through the Lankos algorithm. Again, Deslagina, I'm sorry. I mean, I don't really know how to pronounce it. But that's okay. So we'll go from here. Okay. I think everything is ready to get started too, so we should be good to go. So let's pop this over here to this desktop, pop that to that desktop. We have everything ready here. So what I'm going to do first is I'm going to create a file called lanzos.cpp. Okay, and again, for this, we're going to be using the eigen library. So lanzos.cpp. Okay. This is gonna be kind of difficult, I think. Okay, so we're gonna do this, this, this. Okay. Let's go up. Purpose. And the purpose is going to be to diagonalize. Oh. Yeah, sure. To diagonalize a matrix. Let's say a random matrix. Okay. This should be okay. Okay, so now we're going to go here. And right now I don't have anything else to say, so I think that's okay. Actually, what I should do, just to be as specific as possible, is say using the Lanczos algorithm. Now, for the record, again, Eigen has this done already, right? So Eigen has some sort of diagonalization function, and that's perfectly fine. What we're going to do right now is, just so we better understand how the diagonalization works, we're going to do this kind of ourselves, and then we're going to work on it from there. Okay, so first of all, we're going to include, and I'm going to include IOStream because I know I'm going to need it. Good, and now we're going to include the Eigen libraries. Now, we've done this before, so let me go back and see where we did it before. So one place that we did it before was going to be in, oh, I guess it was in linear algebra, wasn't it? Let's go back to archive. Then we're going to go to linear algebra and conjugate gradient. Here, let's just cd into this directory real quick, because I'm sure there's something in the make file that I need to pay attention to. Let's do conjugate gradient eigen. Eigen. Okay, so looks like we can just do this. So let's do include and eigen. Okay. Then we have CAssert, CMath. We might not be able to, we might not need CMath. It might be fine. Yeah, maybe this is fine. Let's see what happens. So I'm gonna write this. We go over here, I'm gonna write quit. And I don't think I can build it straight up. I think I need some sort of library to read in. So let's go back into our directory that we have here. And it's going to be DMRG. And let me real quickly just create a sudo int main. And by sudo, I mean the actual use of the word, not sudo. So we're going to do g++. 1 second. Then I guess it's just going to be lanczos.cpp. Yep, that's what I thought. So we need to read something in special for eigen. And I don't remember what it is exactly. So let's go and let me go back into the previous directory where we know we were building eigen. And let's see what we got. So we're going to go back a directory and then go into archive and linear algebra. Conjugate gradient, eigen, readme maybe? Archive, linear algebra, readme. Okay, wait, are you kidding me? I always tell you how to build things. So let's go into linear algebra. What? Aw, man. I screwed that one up big time. Okay, where else did we use? Here, let's go over here and let's just say building eigen. C++. Getting started. Man, I can't believe I didn't write how to compile it. I always put how to compile it in the guy. Okay, so it's gonna be G++, path to eigen, my program.cpp, my program. Okay, so where is eigen then? That is the question. Let's see. On Linux, another option is symlink copy, user local include. Yeah, we'll see what happens. I know I've done this before, so let me real quickly go through this directory tree and check something out real quick. So it's probably going to be in the archive somewhere. Let's see, function integrate, bash drop. No, it's not going to be in any of these. cd ... ls, molecular dynamics, invisible lens. I don't think we used it for any of those, but I know we've used eigen before. Maybe it was in that linear algebra stuff. Okay, let's just go back into DMRG, ls, and let's just see if we can build this guy. So here it is, and we want to do, 1 second, lanczos.cpp. Of course, it is not going to find it. So let's go over here and do eigen arch Linux. Okay, 1 second. Let's do source files. Oh wait, nope, that's not what I wanted. Let's do file list. Okay, so it's user include eigen3. And let's see what happens. Okay, so it created something, but it looks like there was a bunch of warnings, which I guess is fine. Let's do clear. And now let's try it one more time. Let me see where all these are coming from. It looks like eigen just has a whole bunch of warnings, which I guess is fair enough. Ignoring attributes on the template argument. Yeah, okay, well, I guess there's nothing I can do about those. Okay, well, let's just see what happens. So, int main. So now what I'm going to do is I'm going to go back into that previous directory that we had before. So let's go into linear algebra. Oh, sorry about that. Archive, linear algebra, then conjugate gradient, eigen. So what we want to do is we want to create, let me see. Oh, well, that was super easy. We want to work with this. So first things first, I think if we just use the namespace of eigen, we should be okay. So using namespace eigen. I don't think it's capital. Is it capital? Oh, it is capital. Good. Okay. So what we want to do is we want to create a matrix 2D. And then I just want to kind of print it out. So let's do, where's conjugate gradient? Right here. So matrix 2D. Let's just create a 2x2 matrix real quick. So we'll do say matrix 2D. And we're going to say it's going to be called A 2x2. Okay. Now we have our 2x2 matrix. Let's go ahead and fill it with random numbers, which shouldn't be so bad. So we'll just say, we could just fill it with these numbers. Why not? These are already set. Drop them down there. And then we want to see out the value itself. So what I'm going to do is I'm going to say see out. And then we want, let's do 4. Maybe there's a better way to output it. Okay, so we're going to go here and we're going to say 4 int or size t I equals 0 to I is less than 2. And it looks like it takes zeros just fine. I plus plus. And then we're going to say 4 size t j equals 0. J is less than 2. If I can hit a semicolon. Then we say j plus plus. And again, I should probably do plus plus j instead of j plus plus. Doesn't matter. Okay, so now we're going to say see out. 1 second. See out. And what do we want? We want a of ij. Then probably a tab or something like that. Okay. And then down here we say see out new line. Good. And I'm going to add an std in here because I don't think we're using the std namespace over here. And now let's do, oh, we are in DMRG. So let's go ahead and run the last g++ command. And error expected semicolon. What did I do wrong here? Yep, that's because that's a comma. Good. Glad we're getting back to our roots here. G++. Good. A.out. 4113, exactly what we expect. Good. Okay. So basic eigen libraries are fine. Let me add in a note here on how to compile. Compile with okay. Go up. Here it is. So it's going to be up here, G++. And what do I need to do here? I basically need to put down a quick note saying compile with for Arch systems. Good. Okay. Write that there. So we have our matrix 2D. Everything is fine. Let's go ahead and create a function for the conjugate gradient method then. So in the end, the conjugate gradient method is going to return back, let's see, it should return back a matrix, right? So we'll go down here and we'll say matrix 2D, and we're going to say, wait, did I say conjugate gradient method? I meant the Lancause. Lancause. Has to be Lancause. So we're going to say lan. There we go. And what are we going to have to read in? We're going to read in, do we have to read in anything? Yeah, we should probably read in the matrix. Now we need to diagonalize, right? So matrix 2D, and we're just going to call it, what should we call it? Matrix diagonalized matrix, D matrix. Tricks. Anyway, it's fine. We'll say D matrix, and that should be okay. Okay, here's our main function. Again, it's not important right now. I'll leave that as it is. And we'll go ahead and create the matrix down here. So again, guys, it's been a while, but basically the way I always do this is I always try to put the functions under main because it's just easier for me to read. So I know what all the functions are up here, and we go there. What I'm going to do here is I'm going to create a very quick tag, just because I like having tags. So here we go here. Oh, I did it backwards anyway. How's everyone doing, by the way? Sorry if today's been a little bit scattered. Again, I just kind of got back after a long trip away, so it might be a little bit rough compared to normal, but that's okay. We'll get back into the swing of things, no problem. If you guys are having any problems or if you have any questions, let me know, and I will do my best to answer those questions as they come up. Hopefully, you guys are having a good, I guess, evening for you guys. Maybe middle of the day if you're in the United States. And good. I guess there's a lot of things to talk about in terms of things going on around the world right now. We could talk about climate change. No, I don't want to talk about that. No, let's not talk about that. Okay. So matrix 2D Lancause. So first of all, this is going to assume that we have the matrix already generated to diagonalize. So we're going to do a couple of different steps here. Okay. Let me get a quick drink of water again. Ah, gosh. 1 second. Okay. So in general, we are going to be generating, let me see, what is it called? The magnitude of R, right? So at every time step, we're going to be generating the magnitude of R, and we continue until the magnitude of R is equal to 0, right? So we just keep continuing. So basically what I want to do first is I want to say, let's go here and do, we're going to say double threshold. And we're going to say, sorry about that, we're going to say the threshold is going to be equal to 0.01. I'm giving it a kind of large threshold, I think, but that's okay. Okay, so we have the double threshold. And now we have a giant while loop that everything's going to be in. So we're going to say while, let's say we're going to call a value something. So we're going to also add a double beta. And we're going to set this equal to, I don't know, 10. Just to be arbitrarily large, which I probably shouldn't do, but I don't really, at this point, see a way around it. So setting beta, oh, sorry about that, beta arbitrarily large for now. Okay, so while beta is greater than threshold, again, we're trying to get this down to 0. We do this loop here. Okay, so what is the loop? I will define all the variables above the while loop for now, or in a bit. which are all defined kind of as you might expect. So like I said before, we have that j value that we have to take into account. And the j value is just going to be basically an integer that we keep track of, right? So we're going to say, maybe there's a better way to do this. Probably, but that's okay. So we're going to go up here and we're going to say int j. And we're going to set it equal to 0. And we know within the loop we're going to have to do j plus 1. Husky, this is Windows 95 actually. A lot of people kind of got into Windows, you know, in like 2000s or something like that, you know, with Millennium Edition or something like that. This is kind of the predecessor of that, you could say. So it's kind of Windows before it was cool, I think. So that's kind of why I use it. Okay, so we're going to say j is going to be equal to j plus 1. And then what do we do from there? Well, this is the whole algorithm. We just add 1 to j every single time. Not really. Okay. So at the first iteration, right, we're going to be generating R. Can it run Crisis? I don't know, maybe. Wait, can it run Crisis? I don't know. Crisis Linux. Oh, it might be through Wine or something like that. Yep, it's through Wine. Actually, I don't even know what Crisis is. I just know it's a game that's apparently graphically intensive that people use as a benchmark sometimes. Okay, so we got to generate R every time. So the first R naught, which I think we should probably read in here. Okay, so let's generate the first R naught. R. Man, I hate having just single-lettered variable names. They're so hard to search later on. So the other day in this code that I was working on, Catten626, no, I'm not on livecoding.tv. I'm only on Twitch right now. I've been asked to go to livecoding.tv, but at the time there was some shady stuff going on there, so I did not go to livecoding.tv. However, I have been thinking lately that maybe I should. It's kind of up in the air, but for now I'm just kind of doing streaming on Twitch. And then after doing streaming on Twitch, I throw the stream onto youtube.com just to say that I did the stream and stuff like that. For the most part, I kind of like the way it's working. The stream is basically to create code that I'll then use on my YouTube channel later on. It's kind of nice. It was just at the time. So the idea was that the CEO of the company, or whatever his name was, well, I didn't even give his name. I just said the CEO of the company. But at the time, this was, again, a few months ago, he had just kind of been trying to recruit a whole bunch of female streamers. Now, I'm not a female streamer, so I was not at all affected by this, but he did something really shady. He said, basically, there was this one female streamer who was on livecoding.tv, and she just didn't want to stream anymore, so she stopped streaming. And the CEO, I don't know if he did it personally or if someone else did it, actually just vandalized the account instead of shutting it down, because apparently, so the girl wanted to shut down the account, but apparently she couldn't do that because, you know, it just wasn't in their system to do that. So he just vandalized her account and said, you know, that she had been banned for one reason or another when she had not been banned. She asked for her account to be terminated. And it was just kind of, you'd expect a site that's all about coding and stuff like that to be a little bit more technically minded. Anyway, that was the only thing. There wasn't anything big there. Okay, so generating the first R value. I don't know what to call the R value at this point. I guess we'll call it, should we call it a radius? Because in a way, it's kind of related to a radius. What do they call it over here? So we say B is equal to R naught. R0 is going to be equal to A minus alpha. No, that doesn't help at all. So we're just going to call it gamertag envy. What kind of codes are you looking for? I don't know what you mean by what kind of codes am I looking for, but in general, this particular channel does computational physics. So we do physics algorithms, and we do basically I know, I don't know. We do the physics algorithm, and then later on we put the algorithm on YouTube or something like that. It's, well, okay, I say we do that, but I haven't actually done it yet because I'm kind of behind the time. So I've been working on one thing or another. But generally physics algorithms. So if you have an algorithm that's about physics that you think is really cool, or some sort of physical phenomenon that you want to learn about, let me know, and we could probably do that later. There's actually one, gosh, sorry guys, sorry for the sidetrack, but there's one called a Hofstadter butterfly, which I'm currently trying to figure out if it's simulatable. So this guy right here, oh, that's a horrible picture. One second, let me go to images. There has to be a pretty good, here it is. Here's a pretty good image. Okay, so this is called a Hofstadter butterfly, right? The idea is that magnetic field is on this axis over here, this bottom axis, and energy is on this axis here. If you take, let's say, any atomic system and you have an electron or electrons in the atomic system, the idea is that the electrons kind of move in weird patterns, and these patterns are sometimes called block waves, and we could talk about that when we do the actual simulation here. But the idea is that as we increase the magnetic field, we generate these really cool, what are actually fractal effects. So if we look in here, if we keep looking in and we keep zooming in further and further, we're actually going to generate in real life a fractal that continually regenerates itself over and over and over again. And I really wanted to see if there's a way to simulate this, because the Hofstadter butterfly is actually really cool. It's one of those things that, like, when I heard about it for the first time, it completely blew my mind. And I wanted to kind of, you know, tell people about it. I thought it'd be kind of fun. Anyway, so this is one of the other things that I kind of want to simulate, along with the dusty plasma stuff and all the other stuff going on. So, I don't know, just if you have anything cool that you see that's physical and you think, oh man, I'd like to learn more about that, let me know. And that's kind of the point of this channel, just to learn more about physics, kind of together, me and you, physics to the end. Yeah. Okay, so we're going to say R is going to be equal to, what they set it to initially is some sort of random value. So basically what we need to do is we're going to say that R, which is going to be a vector. Oh, what did I just do? What am I doing? Oh my gosh. Okay. So we're going to say it's going to be equal to a vector of some sort. So we're going to say vector. I think it's just a 1D vector. Yeah, let me see. So I should have a vector in here somewhere, right? Sure. Vector 2D. What is the difference between a 2D and a 1D vector? I guess I'll just do vector 2D. We'll see what happens there. Okay, vector 2D. We're going to call it R. Is going to be equal to... Oh, it's not going to have anything in it right now. But it has to be of a certain size. So let's see, how did I create the vectors to begin with over here? So let's go into vector again. Vector 2D. Vector 2D. Here we are, R and P. R naught is equal to P minus A. That's fine, but that's not... Sorry about that. That's not what I want there. P0 is equal to R0. That's fine. Ah, come on. United, we are physics buddies. Cool theme song. Yeah. Okay, it looks to me like I just need to generate... Where's B? B of 0, B of 1? Oh, can I just do it that way? Alright, I'm going to try something here, guys. Okay, first of all, I need to find the size of a matrix, of matrix 2D. Now, I know the size of matrix 2D, D matrix, because I read it in. However, let me go to eigen. Eigen, find size of matrix 2D. The matrix class. Let's go to size. Fixed in it. Oh, well that wasn't what I was expecting. It's all the way down here. Okay, so let's do the next one. Size is unknown. Nope. Should be something in here. Should be like dot size or something like that. I'm just gonna guess it's dot size. Do you think that's a bad idea? Just to try dot size? I'm just gonna try it. What's the worst that could happen? We're gonna try this. 1 second, I'll take a look at that gamer tag. Just let me go ahead and comment this out for now. And compile it real quick. After doing this. std cout, and we're going to do a dot size. This is a really bad idea. Okay, write this, go over here, write and quit. And now let's do g++, a dot out. Oh, it worked. Okay, solve this. Open link. Let's see what it is. Science news, context. The world is a computer, life is an algorithm. This isn't the type of stuff I can solve on this channel, unfortunately. The idea here is that it's not saying that, how do I put this? It is, first of all, not something to solve. This is a an opinion piece, I think. And the other thing is, it's probably describing some sort of biology that I'm not aware of. I don't do very much biology, so I'm not very good with this. But this is actually kind of a neat thing. Each pixel of the cellular automation can be either white or black, corresponding to 0 or 1, as in the binary math used in digital computers. Applying simple rules can result in complex patterns. Fair enough. Cellular automata may offer the algorithmic power to mimic the laws of physics and the evolution of life. Yes, sure. That's totally fair, but it's totally vague. I don't have anything to work with. Yeah, so what I would need, write in their paper. If I have a paper, that helps. Self-referencing cellular automata, model of evolution, information control, and biological systems. This might be usable. What do we have here? Oh, well. Yeah, okay. Anyway, so this might be something that I look into. Which is the paper where that was referencing, right? So once I have a paper, I have something that I can actually work with. It's kind of hard to work with pop sci or opinion pieces, but that's okay. Because they sometimes will link the paper, and when they do, that's perfectly fine. Okay, so a.size output 4. That's fine. But what does that mean? That's a number of elements? So I need size of x. Yeah, so I think that paper should help a good bit in understanding, but this didn't help at all. Let me see, matrix double, ASCII quick reference. No, why do I want any of these? Length of x? Oh, c.rows, of course, rows and columns. Ah, what am I doing with my life? So we'll do rows. So we'll do g++, a.out. There we go, that's what I want. Okay, rows. So now what we're going to do is we're going to say for size t, I is equal to 0. Then we're going to do I is less than d matrix dot. And it doesn't matter, rows or columns are both fine here. We're going to do rows because rows I think makes more sense. Then we're going to go here. And then all we need to do is generate a random number for each of these guys. Now, here's the thing. I've had trouble with random number generation on this channel before, but I've done it on this channel before. And so what I'm going to do is I'm going to go down here and I'm going to create, well, actually, how do I do it first? So let's go here, open up a, let's do MD, and let's see, what do I have here? Daemon. Okay, good. So nothing there. So we're going to go into archive, MD, daemon, and then we're going to, daemon.cpp. And there should be a random number somewhere in here. Random, that's fine. Good. So create only one random device. That's fine. And let's see, where do we actually do the random? Let's do rand. Seed, static, empty, generate seed. Okay, that's fine. But I only need one random number. This is my first time watching something like this, and I'm starting to like it. Ah, good. I enjoy it. I'm glad you like it. And again, if you have any questions, let me know, because we're kind of moving at a weird pace today. I feel like we're moving slow, but we might be moving fast for people who've never seen this kind of stuff before. Okay, so we could do this in a number of ways. What I want to do, I think the tree command could help you. I thought tree just does... Yeah. Oh, actually, you're right. That would kind of help, but not what we need right now. Okay, so linecons.cpp. Let's go down here. It's so nice to watch someone doing something they're passionate about. Ah, thanks, Cat626. Okay, so now we have random device. So in order to generate random numbers in C++, which I always freaking forget, but in order to generate random numbers in C++, what we need to do is we need to generate a random device, and then we need to work with the random device with some sort of distribution. In our case, we want just a standard normal distribution, right? So uniform real distribution should be perfectly fine. And then we give it kind of, I guess you could say, how many numbers we want to work with, or the size of the numbers that we want to work with, right? So it's going to say we're going to be picking a random number from these two things, right? So we say, here's our x, here's our y, or here's our 0 and 1, and then we go from there. So let's go here, and let's go ahead and generate the random device. So first things first, I need to go up here, and I need to create the device for random. So creating random device. Okay, so then it should be static, standard, random device. 1 second, random device. What am I doing? Okay, RD. Then we go down here and we say int seed, which of course has to be an integer, seed. And this is going to be equal to our random device, just some sort of function from the random device. And then we say static, std. And what we're using is what's called the Merlin twister algorithm, which actually might be fun to look into one day, just to do on stream, kind of like we're doing with this one today. And then we're going to do gen seed. So what this is doing is we're using the Merlin twister algorithm, or rather, yeah, that's fine, to generate our seed appropriately. Let me see. I had this down at one point. Yeah, the seed is related to the random device. Okay, this is probably fine. Now we need a uniform real distribution. And so what I want to do, uniform real distribution, box length distribution. So let's do something similar here. So we're going to do uniform real distribute. Oh my gosh, what am I doing? Uniform real distribution. Okay, and let's go here and add an std at the front. By the way, guys, I don't know if you've ever used a Mac before, but if you've ever used a Mac, it makes you learn Vim very well. So for example, I did not know before this, I always press the home or end button to get to the first and start of every line, but you can actually press 0 to get to the start of every line and $sign to get to the end. Just for the record, in case no one knew that, I learned that, and it's incredibly useful. Oh, uniform real distribution, we need it of doubles. So we're going to do double there. And what should... Thanks for the semicolons, chicken skill. Okay, so now we do double, and what do we want this to be of? So we're going to want this to be of some sort of random distribution between 0 and 1. So I think, unless I'm completely wrong here, we're just going to say, I'm just going to call it dist. And I'm going to say it's between 0 and 1, but I think it should be standard to be between 0 and 1, but it's okay to define it, I'm sure. Okay, so now we go here, and what we basically did here is we created some sort of, I and A is fun too. Oh yeah, insert at the start of the line and at the end of the line. Hold the F1 button for 15 seconds. I don't think that does anything. No, I'm not going to try it, but I don't think it does anything. Okay, so now we're going to go through each of these elements, and we're going to say, okay, R of the element that we're in, R of I, is going to be equal to some number from the distribution, right? So in order to call the number from the distribution, let's just go here, and let's see how we did it before. There we are, come on. I know I've done this before. Why didn't I just... Okay, that's fine. Okay, so what I have here is I'm going through all the distributions, and I'm saying, yeah, exactly this. So let's see what happens if we go here, and we say R is going to be equal to distribution of gen. G++. Good. Okay, great. Didn't work. Okay, that might be because I screwed something up. So let's see, what do we have here? I is listed. Well, first of all, the for loop, because I'm a complete and total moron, does not actually have a ++ I in it. There we go. That's one thing. Okay. Next, gen is not declared in the scope. That is because I use gen though. Dist is not distribution. Wait, those are declared. What? Are they not declared? Wait. Let me see, what did I do before? So I thought this is exactly how I did it before. So let me do random. Okay, so SCD, random device, RD. We said it was Merlin Twister Gen Seed. Yes, so it looks like we had defined them. Okay, but it says we're not defining them. So why are they not defined? Max velocity distribution, uniform real distribution. That all seems fine. Distribution. Dist of gen. How did we use this before? So let me do box left. Okay. So we say is equal to box left distribution of I. Okay, so we're saying that that element, R of I, yeah, that should be perfectly okay. So for auto position in P.P position, for auto P, and oh gosh, maybe it's not okay. Box left distribution gen. Why is it not defined? Okay, let me try some things real quick. First of all, let me see if I can generate a vector that is of an appropriate size already. So let me say generating vector in eigen that is of a certain. This is not how you Google, by the way. Length. Okay. Advanced initialization. Oh yeah. Okay, so M vec1. This isn't what I wanted. Joined vec1 3. I just want to generate it that at a certain size. Matrix class. Let me see. Oh, float 4.4. Vector. There we go. Float 3.1. It's got to be it. Okay. Let me see what happens if I do matrix. Oh, wait. That's. Should I be using? It looks to me like for vectors, they're just doing a one-dimensional matrix, which is perfectly fine. Not a problem with that. Let's do that. What's the difference between matrix and matrix 2D? Gosh darn it, I don't remember. Matrix versus matrix 2D eigen. Okay. What do we have here? Matrix 2D A. See, they're using matrix 2D. What is a matrix class? Oh gosh, this is exactly like every other one of my episodes, where all I do is kind of fiddle around with things until I figure out something that works, and then it doesn't work in the end. Matrix 2D is a 2x2 square matrix of doubles. Oh. Well, we probably don't want that then. Yeah, we probably definitely don't want matrix 2D then. Yeah, I was incorrect. We probably just want matrix. Okay, so we're going to do this. Matrix 2D is automatically 2x2. So let's say we want to generate something that is of an appropriate size. We're going to say int, and then we're going to say 2, 2. And I think that should be right. So let's write this. And now this is not going to compile because it doesn't like my gens or my dists. So I'm just going to comment this out real quick just to make sure that the top part is working as we expect. And then we'll go from there. Oh my gosh, this is good. This is good. This is good. Okay, so let's do a.out. It's working. Okay, so now let's see what's happening with these random devices. Okay. First things first, what I want to do is I want to do vector 2D. Rather, I want to set this as vector. How about let's just make it a one-dimensional matrix. So we're going to say matrix, and it's going to be filled with double. What do we want? We want double. We want one dimension. Now, is this columns or rows? 2x2 square matrix of doubles. That's fine. Vector of 4 floats. Okay, they say to do vectors this way. So we're going to do R, and it's going to be D matrix dot rows, and then this is going to be 1. So this is officially a vector now. Good. Now when we go through here, I'm actually going to change the way I do this. I'm going to do auto. For auto. And we're just going to call it R We're going to call it I, because I'm so original with naming. And then we're going to say auto I in. Then we want to do R of just the first element, right? So we want R of... 1 second. How do we do this again? Because I'm an idiot. I can never remember how to do freaking... Oh my gosh. Sorry about this, guys. So we're going to go back to the random device, because I know down there we had something like this, auto P. Okay, so it's going to do auto at I, ampersand I, for R. I don't know if this loop is going to work either, so we're just going to try it. In left data. Actually, I've got a feeling it's not going to work. So let's just keep it the way it was before. Size T, I equals 0. I is less than... What are we doing? I is less than what? Should be dmatrix.rows. Besides, this is easier to read anyway, right? plus I. Okay, so now we go down here and we say R of I. R of I, and of course 1, because it is... Oh, or 0, I guess. Maybe it's 0. Is equal to dist gen. Okay, so now how are we doing this? Max velocity distribution. Box left distribution gen. Am I doing something different here? Because it looks to me like it's the same thing. We generate the seed. We then, after generating the seed, goes through and say, create a distribution, and we run gen in that. It looks the same to me. What am I doing that's different? So let's go over here, right quit, and let's do this to G++. Okay, so now we have a whole bunch of other issues. STD random device is not... Oh. Okay, so let's see, what do we have here? Error, call nonstop function, dmatrix.rows. Let's see, what's the problem? Let me say, let's go down here. Oh, come on. And let's say size. I guess I'm going to generate it down here. Size is going to be equal to dmatrix.rows. Okay. We're talking I. Thanks for coming in. I'll see you around, man. Have a great evening. Okay, so let's do this. Oh, what am I doing with my life? Okay, there we are. dmatrix.rows. Then we'll go down here and we'll change size here. As you guys can see, I'm super rusty. This was not supposed to take this long. Size. And let's go here and change this to size. I don't even know what language I'm coding in anymore. Okay. G++. Okay, size. Error, the value of size is not usable in a constant expression. Really? See what happens here. Okay, well, apparently I need an actual number there, which is weird. I mean, I guess it's fine. It probably needs to know on compile time. So let me do a couple things then. Since this is actually compiling, and let me say, let me add in a note. If I can spell note. Check later 10. Check 10 later. There we go. Write this. Okay. So this seems to run, which is great. Now let's go through here and let me check to make sure I have everything the way I want it to be done. So let me generate a couple of new matrices. So we're going to do matrix. And then I want to do it of doubles. Let's do 10, 1, and let's set it to, I'm just going to call it Q. Why not? Okay, so it's going to be called Q. And what do I need to do here? It's called Q. I want to check a couple things. So first of all, how do I initialize it all to be 0? Let's see, rows at compile time. Oh, that's not going to help me at all. Initialize matrix at 0 eigen. Advanced initialization. This isn't exactly what I wanted. Oh, here we are. Fixed array. Let's see. Array 33f a1 is equal to array 0. Two-dimensional dynamic. Ooh, that helps. Oh wait, what am I doing here? One-dimensional array. Array. What is the difference between array and matrices in eigen? I'm not actually sure. I have no idea. Okay, so that isn't quite right. Array and matrices. So here we have matrix 3f. Doesn't help. Okay, let's see, what do we have here? As so often happens, I found the answer in the docs within 30 seconds of posting. Eigen matrix xt mat is the matrix constant. Okay. Okay, that's fine. Eigen matrix constant. Okay. IJ. Mat block IJK. Okay. Let me see if I can figure this one out. So eigen matrix constant IJ1. So this is setting all the values to 1. And it should be IJ must be the size of the matrix, I would guess. Okay, so let's try generating things in this way. So let's do, instead of doing it here, let's do Q. And let's say it's going to be of this size. 10, 10. Let's do G++. Okay, that one seemed to compile just fine. And now let's just set it equal to 0. G++. Okay, that one also seemed to work. So let's go down and let's just say for I... Oh, maybe I can do an auto here. Auto at I is equal to... How was I doing it before? What would I be autoing through? Just all the elements, I suppose? Nah, it's not worth it. Let's just do for size t, I equals 0. Then we're going to do I is less than 10. Then we're going to do I++ or plus I. It doesn't really matter. I'm kind of transitioning from one to the other. Now what we're going to say is std cout q of I, why not, II. We're just going to print out the diagonals here. Then we're going to do end line. Okay, let's go over here, G++, and let's do a.out. Huh. Did I do something stupid here? Did I write it? G++, a.out. Okay. It's not couting anything. Cout a.rows, n. That's fine. 1 second, let me think. Why would it not go through this? What? std cout. What? 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 I don't even know. What? Okay, let's try this one more time. G++. A.out. It's not even... What? Int main. Okay. It's printing this out. It is printing this out. It is printing this out. But for some reason it's not... What? Rank quit. ls. vi. Clearly still there. Okay, let's do G++. Line codes. What? Remove a.out. Compile it again. A dot out. Oh, did I do something stupid? ls. I compiled it. Oh, is it not compiling? Maybe it's actually not compiling. Oh, there we go. The errors are all the way up there. I spent like the past 3-4 minutes trying to figure out. Okay, Q is not declared in the scope. Q error. Yeah, of course. Yep, that would be an issue. Okay. Q error. Yep. Okay. So all those same Q error. Okay. Good. Okay. Let's do matrix double. Yeah, okay, same problem. But I know we've done something like this before, so let's go back a little bit to, let's do archive, linear algebra, and of course, well, of course, I say of course, but I don't actually know what I'm doing. Conjugate gradient, let's do eigen. Okay, so we generated matrix before, matrix 2D, A of 2, 2, which is fine. But these were all vectors 2D and matrix 2D, right? So it's just 2D matrices. So what do we need to do? We need to generate a randomly sized, okay. Generating matrix of a, let's do eigen. Let's do initializing. It's probably a little bit better. Well, it should be under advanced initialization. Okay, matrix 3F M, and we give it the values. That's fine. I just want to initialize a whole bunch of values to 0. Matrix A, 2, 2. Well, it's letting them do that. Why would it not let me do advanced initialization, matrix class? Okay, let me look for initialization. Uninitialized, matrix XF A of 10, 15. What was the exact issue I was running into? Oh. It says treated as a compound expression. Expression list treated expected a semicolon. Okay, well, let's see what happens if I just do this. Write this, go over here, G++, error, Q cannot be used as a function. Okay, that's fine. Expression is treated as a compound expression initializer. Wrong number of template arguments. 1 should be at least 3. So again, we can do this, where we do double 10, 10. Equals Q, which is fine. Now let's do an A dot out. Yeah, and they're all 0. That's fine. Okay, so let's go up here. Let's remove this. And let's remove this. Okay. Now, here's the question. Why can I still not do this? Okay, so for some reason, I'm not going to be able to generate this the way I want to generate this. I want to be able to generate it like this, right? But I don't know why that's not working. What's XF stand for? Matrix XF? Oh, I see. Must be a dynamic. Okay. So what I'd want, probably, yeah, XD. That's what I want. Matrix XD. So let's go here. And let's do matrix XD. We're going to say Q of 10, 10 equals 0. Over here, G++. Oh, okay. Well, let's try this. G++. Okay, that one worked. Fantastic. Now we just have to figure out how to initialize an XD matrix to all be a particular element, which I guess isn't that important because it's all initialized to be 0. Yeah, I guess if it's all initialized to be 0, I think it should be fine, right? You guys okay with that? I think everyone's okay with that. It's fine. Okay, so now let's do 1, and let's just try this. This one's going to break, pretty sure. Oh, it didn't break. Fantastic. Good. Okay, that's all I needed to know. So now we can go through here, and we can do this. R of I is equal to dist gen. Now let's see what happens if we don't return a matrix 2D. Let's actually return a matrix XD. And up here, let's also return a matrix XD. Okay. By the way, did anyone ever... So there's obviously Disney Channel, right? And then there's Disney XD. Does anyone know why it's called XD? I have no idea. But it's been kind of bugging me, you know, because you'd think, you know, Disney X, okay, that's fine. But XD, I don't know what the D is for, you know? It just doesn't make any sense to me. Okay. So it looks like we're generating everything just fine. Let's go through here and let's change this guy to be something reasonable. So we're going to say matrix XD again, and we're going to say R of, what do we want? R of D matrix dot rows, and then 1. Write Y XDTF. What? Write Y XDTF. I'm not sure what you mean. Okay, it all seems to compile just fine. So now what I want to do at the very end here is I actually want to return R. And I'm going to comment this guy out. For now, just to make sure that everything's working and that the function is doing what we expect. Okay, it looks like this took a lot longer than I expected, and I'm terribly sorry about that. So let's go up here and say matrix XCQ. Yeah, this should be fine. Is going to be equal to the F is XD, right? Disney XD. The F is XD. Maybe. Okay, this is going to be equal to Lancause. And then we're going to read in a matrix. 2D. Do we have a matrix? Should be matrix XD, actually. Good. And we're going to go down here and do matrix XD. Oh, you know what else we probably used eigen for? No, we used Julia for that. Not sure. Okay, so let's go ahead and create a random matrix, int22. Oh, wait, no, we have the matrix. So we're just going to read in A. And it's going to be A here. And I think that's all we need to read in. And now we go through q.rows. Go over here, G++. Okay, so it looks like we had a problem with G, which doesn't make any sense because... Oh, now it does? And G's kind of look like C's, but I screwed that one up. Oh wait, I needed Q. What the heck? How did I get G? I'm looking at my keyboard right now, and G and Q are so far away. Okay, that's fine. Whatever. G++. A.out. Okay, that one seemed to work just... Something broke, so it didn't work out just fine. Error, static assertion failed. You mix different numeric types. Static assert. Okay, what do we have here? Let's go ahead and clear a couple times. If I can spell clear. This is really working out differently than I intended. Okay, let's go up here. So it looks like the only error we have is this one, which is static assert.h, which doesn't help me any at all. So this error message is not really, it's not really going to help me any. So let me see if we can figure out the problem. Eigenstatic assert. Note the expansion macro eigenstatic assert. 11. Nope. That doesn't help either. Okay, so what do we have then? Clearly I did something wrong here. Let's see what happens if I just comment out this part. Comment out this part. G++. See, now it works. Okay. So clearly the problem is in the assignment here. So we do matrix XD Lancause. We're going to DD this, and let me see what happens if I do this. Just comment out this for loop at the end. This shouldn't do anything. This should still give me an error. G++. Yeah, it still gives me an error. Okay. So dd here, dd there. And now let's just do some things then. What I want to do is I want to just create R. And then return it. And should be, yep, so everything else should be deleted. Let's do this here. Okay, this one still gives us the same problem. So I guess the problem is in returning matrix XD. I feel like that might be the problem. Which is weird to me, because you would think, let's see, matrix, oh, wait a minute. Maybe that's the issue. Maybe this needs to be a matrix XD. And it's going to be A, 2, 2. That's how you generate them, right? Yeah. Okay, let's see what happens now. Yeah, okay, that works just fine. Good. Let's go ahead and DD here. DD there. DD there. And go here and add in this guy again. I've gotten nowhere in 2 hours. This is, I guess, typical for programming, but that's okay. So now what I want to do is write this, go over here, try it one more time, make sure everything is working. Good, so now we have 2 random numbers that are of a just whatever size. Doesn't matter so much. Okay, so we have, after all of that work, finally random numbers being generated in the way that we want them to be generated. So now we have to work on this while loop. Let's see, what should I do for now? I think we'll work on this for the next 10 minutes. Again, guys, I typically end the stream at 7 o'clock in the morning, my time. So we're getting there. It's 6:46, so we have about 10, 15 minutes left. Okay, so what do we need to do? Well, in this loop down here, we need to say j is equal to j plus 1. That's perfectly fine. And then we need to calculate some sort of beta at some point that needs to be less than threshold. So how are we going to do that? They suggest creating some sort of alpha or something like that we work with first. So let's do this. So it says alpha is going to be equal to q. Oh, we haven't generated our q yet. Let's kind of use, let's go one step at a time. So we have our r, right? Now what we need to do is we need to go through and look at some stuff. So r is being generated. So now let's generate our b value, which is going to be a, I suppose, matrix XD. So we're going to do the same thing here. Do matrix. Probably do it here. So we'll do B of D matrix dot rows 1. Okay, what else do we need? We have B, we have Q, of course, of D matrix dot rows 1. Good. Okay. What else do we have? We have B, Q, A. But A should just be a scalar, I think. No, we're multiplying it by the big matrix A. Okay, so what I want to do there is I want to say, sorry about this, guys. Oh, that wasn't what I wanted. I'm going to have a little a. And again, this is just following the notation from the book that I looked at, so it's probably not the best notation. D matrix dot rows and D matrix dot columns. I'm hoping I'm doing this right. I might have mixed up the rows and columns, but that's okay. Okay, let's go through and work on each of these one step at a time. So we're going to say B is going to be equal to, what do we want B equal to? It should be the square root. Oh my gosh. B is a double. That's what I get. Okay, so where are my doubles defined? Double here. So we want... Oh wait, is B their beta? It is. This is me being an idiot. Eta. Okay. So now we have B is equal to this. What else do we need? It's going to be equal to the square root. So let's do square root of, and then it should be R times R transpose. So let's go through and figure out how to do transpose with eigen. Oh, what if we can just do the magnitude? Okay, magnitude. Member functions in eigenmath library for vector magnitude. You want norm. You want norm, note that that's square norm dot normalize. What is the difference? Okay, just show me the mathematical operation that you're doing here. Returns an expression for the quotient of this. Probably not what I want. You want norm. Okay, let's see. We can check this real quick because we'll know what the normalization is of a particular guy. So let's go through and let's check this real quick. So I think it will be dot norm. So let's do r dot norm. Okay. So what I want to do real quick, I want to go here. I want to make sure it compiles, which it does not. dmatrix.columns, of course, I need a parentheses there. Oh, I'm so far behind where I wanted to be. Okay, that's fine. We have our matrix XD, this is 2 by 2. So let me see what the norm of that is. It should be... Oh, why don't we just make a matrix XD that's 1 by 1 and do the norm of that? Because that should be the square root squared, which should be the same number. Okay, let's try that. So we're going to go here. Matrix XD. We're going to say n, and it's going to be 1 by 1. Should be fine. Oh, except there shouldn't be an equal there. Okay, now we go down to the bottom and we say n of 1, 1 should be equal to 5, and it should be 0, 0, I just realized. Okay, and now we're going to say cout, std, cout, n.norm. End line. Let's go here, G++. Oh. Calls. Okay, there we are. Here we are, calls. Write this, go over here, G++. Then we should be able to run it. Oh, shoot. It's an infinite loop right now. Let's go down here and let's remove the infinite loopness of it. Infinite loopiness? Infinite loopiness. Fine. Oh, shoot, I just ran the infinite loop again. Okay, we're gonna go here, a.out. 5, okay, that seems fair. So let me think, what would the norm be of like 5, 5 or something like that? Let me think. If we do the norm of 5, 5, it should be 5, 5. Here, let's just do it very quick. Here we are. Page, new page before. Okay, so we're gonna have 5, 5. And it's gonna be multiplied by 5, 5. So it's gonna be 5 times 5 is 25 plus 25, which is going to give us 50. So the norm should be the square root of 50. Yep. Which is going to be, I don't know, 5 times 5 is 25. The next one is 49. So it's going to be around 7. Okay, so this should be around 7. Let's check to make sure. Just so I'm not a complete idiot here. So we're going to put this as a 2, which should be 1 row and 2 columns, so it should look like this. So I guess it should be the other way. Let's do 2, 1. And we're going to say n of 1, 0 is going to be equal to 5. Okay, n.norm, and this should be around 7. 7.07, there we go. Oh wow, 7.07. It's pretty cool. Okay. Good. Okay, so we know that the norm does exactly what we want. That is fine. r.norm. Like, what's the next thing we need to do? Oh my gosh, we're so far behind. Okay, so now we have to generate the new r, right? And we're gonna say, or we could generate the new a. Ooh, what should we do? We'll generate the new a. Which is going to be equal to, do we have our q yet? Q equals 0. No, we don't. Okay, so we need to generate q first. So q is going to be equal to And I'm going to try something. I don't know if it's going to work. Let's try r divided by beta. And now you might be asking yourself, why wouldn't it work? Because that seems fairly obvious. Okay, it seemed to work. Good. And for now, what I'm going to do, guys, is I'm going to comment out this loop. And I'm going to substitute in a for loop. Then we're going to do... What am I doing? I is less than size. Then we're going to do plus I. And the reason I'm doing this is because this while loop is an infinite loop right now. So we have to do something that isn't an infinite loop. Okay. And now I'm just going to see out I, std, see out I, and line. Go over here, and g++, a dot out. Let me do... I is... g++, a dot out. Okay, good. That's fine. So now it seems like it takes q just fine. Let's go over here and let's see the next step. So we have q. Now we have to generate our final one, which is a. And a is going to be equal to... it looks like it's q transpose times a, big A, which in this case is D matrix, then times q again. So let's see, transpose an eigen. Okay, what is transpose? Adjoint is just transpose. Let's see what happens. So we're going to do q dot transpose times D matrix times q dot q. No, it's just q. Okay, over here, g++, a dot out. Something's happening. I don't know what it is. Okay, so now we have to regenerate r, I think. And we're going to say that r... Okay, yeah, that should be fine. So then we're going to say... Where are we? You have to regenerate r. We're going to say that r is going to be equal to... should be... Oh, that's a pain in the butt. It looks like it's A, so D matrix minus beta minus Q. Okay, so let's see what happens. We're going to say it's going to be equal to D matrix minus A times the identity matrix. Ah, come on. Identity matrix eigen. No, eigen. Not what I wanted. Eigen C++. Let's do the identity matrix. Control F. It also means how to get spatial matrices such as the identity matrix. That's fine. Calling identity. Where is the identity matrix? Is the identity matrix... I thought you told me. It doesn't tell me. Identity, set identity. Oh, is it just set identity? Oh, well, now I'm going to have to check, aren't I? Okay, so let's go over here. Oh, we have 2 minutes left. So it's going to be A times identity. Times Q. Oh. Well, no, that's interesting. Q minus beta times Q. That doesn't seem interesting, but there's something interesting about it. So let's go up here and let's see if we can generate an identity matrix. Yeah, so we'll see if we can generate an identity matrix real quick. Okay, misspelled generating, but that's okay. Tohoda Kila, thanks for coming in. Edge226, hey, how are you? Okay, so what do we have here? Let's very quickly generate, I guess you guys are together a lot. Identity, set identity. I think it looks to me like they set identity for the top right corner or something like that. So maybe, let me see, what do we want here? I think I was in the right page. So let's go here, identity, and what do we have? Yeah, so it seems like they have this set identity thing, which is fine, but I just want the identity command. So let me see what we have here. Yeah, that's what I want. So matrix double identity. Yep, this should be fine. Okay, let's see what happens. So what I want to do is I want to do std. Wait. I can just see it out like that? Holy cow. Good low-level-ish content. Yeah, I guess that's fair. Unfortunately, you guys caught me at the very end of my stream. I stream from 5 to 7 o'clock a.m. Japanese Standard Time every day. So you are at the very end. But tomorrow we'll be picking this up again. Again, same time, same place. So then I want to do matrix. Can I do XD, you think? Well, let's try XD. But I think it's fine if we also do it this way. So let's do double 3 identity. And end line, I guess. Let's go over here, G++. It seems to run. Okay, no it didn't. There's clearly an error in here somewhere. Wait, was there not? Oh my gosh. Clear. I appreciate that. Let's do G++. See, it seems to compile just fine, but we're clearly not outing anything. 1 second. Let me see what happens if I say... What the heck? This is exactly what they say to put down. 3, 4, oh. There we go. There's our identity matrix. Fantastic. Okay, so we have our identity matrix. So then I guess the question is, can we do it this way? Let's try matrix identity of, and let's give it some random values. Over here. Oh, sorry about that. G++, a.out. No, that one had an error apparently in the... See, that's the thing about eigen. Every time I compile it, I can't tell. There's so many... See, there we are, right? That's the problem. So maybe I have to do matrix XD, which I guess should be fair. Let's do G++, a.out. There we go. That's exactly what I want. Okay, so then all I need to do is go down here, and I need to say, since A is of that size, I need to go ahead and create the identity matrix up here. And we're going to say matrix XD, and we're going to say identity is going to be equal to matrix XD identity. Then we're going to call a.rows. Actually, we should probably call dmatrix.rows. And dmatrix.calls. Okay, let's see if this runs. And then... Oh, I forgot the last parentheses. And then this should, I think, compile just fine and work by commenting this guy back in. Let's do G++. Okay, well, it runs just fine. Now the question is it actually doing what we want it to do? Unfortunately, guys, it is 7:04 in the morning. This is actually a few minutes after I typically end stream. Again, I stream from 5 to 7 o'clock a.m. every day, Japanese Standard Time. So, tomorrow, we will continue working on this. I don't think there's much left. We did most of the coding today. What I'm going to do right now is I'm going to go ahead and commit this to the GitHub account that we have for this channel. So we'll do git add lancause.cpp, and we'll do git commit. Then we want lancause. Oh, let's do git commit. As you can see, I need a better git ignore file. That is perfectly fine. So what are we going to say? I added the structure for the Lanczos algorithm. Will test tomorrow. And there we go. So we'll do git push. And just a few quick notes before we leave. Of course, this is all found on the GitHub Simuleos. If we click on this again, you'll see 298 commits, added structure for the Lanczos algorithm, and you'll see that we did about 100 lines, which is fair enough. What is this? I changed splitstep.jl? Oops, I don't think I did that today. Anyway, so we added, 80, 90 lines or something like that. And that's pretty good for an hour or so worth of programming. I'm pretty happy with how this turned out, considering that I have not used eigen very frequently, and I should probably use it more frequently. Again, this is just for diagonalization, so in the end, even though we're writing this now, it's basically to get an idea of how this algorithm works. We're probably going to be using standard eigenfunctions to do the diagonalization from now on. What else is there to say? Let's see. Again, I'm going to post another poll on Twitter today to see what you guys are interested in. Today was magnets. We didn't actually get into DMRG, but we will in the near future if we continue working on that option. We, of course, could continue the subroutines webcomic, which we started yesterday, or we can work on some Dusty Plasma research or other. Just let me know what other is if you're not interested in any of those ideas. Again, this episode will be put on my new YouTube channel, Simuleos, different than Laos OS, which is the main channel, which I'll be working on, or I'm working on right now. I'm making projects to put onto the main channel. These streams are just going to be put on the Simuleos YouTube channel, and I will probably put that up soon. I should probably put a link up on Twitter when it's done. The problem is real people that I know follow me on Twitter, and it's kind of awkward to post stuff that I do online when real people know about it. Anyway, that's all there is to it. Thank you guys so much for watching. As always, have a great day, night, afternoon, morning, evening, whatever time it happens to be your time, and I will see you around next time for the next episode of Simuleos, where we continue working on this algorithm, finishing it up probably in the first 30 minutes to an hour, and then working right on to the DMRG algorithm, which I don't think should take too long, but should be a lot of fun. Anyway, guys, thanks again for watching. See you next time. Bye, guys.